Right, so this is a lecture on practicing for the peer review assessment of week 3. In the peer review assessment of week 3, you'll be fitting data by changing the parameters on a function. So the function in this case is a circle, and the data are corrupted data from an original circle. So we know that the data can be fitted by a circle. And the only point is to try and get the circle with an adjustable radius and center so that it fits the given data as best we can. So we start by making a parametric plot. The circle will have a given radius and a position, and those are the things that we can actually change. And so we adjust our plotted circle by hand until it fits the data set. Okay, so the first thing then is to plot a circle with an adjustable radius. So what we'll do is we'll make a function, and the function will plot the circle with radius r and with center x0, y0. We'll be using plots. We'll use parametric plotting, but just using the plot command, as you see here. There is a way of doing parametric plotting directly in plots, but we won't go into that. If you're interested, you can read up. So the idea of a parametric plot is like you're following the curve as if it is being traced out in time by the tip of your pencil. So you need something that plays the role of time, and we will use t, but t will go from 0 to 2 pi, which is the radians in a full circle, and we will be using the cos of t and the sine of t. So it'll just be r cos t, sine cos t. As t goes from 0 to 2 pi, we do the whole circle. Okay, so that's in this function, trial circle with radius r, x and y component to the center. We run that, so if we set up, we get a generic function with one method. And if we now try it out, we see that we have a circle. Not such a great circle, but it's there. Let's just try this out a little bit. We want to make more than one circle on top of another. So what we want to do is to do something like plot bang, where we modify the plot, we keep the old plot and we add something new, and we want trial circle bang. So you have to write a new function called trial circle bang, which uses plot bang. And if we do that, we set up our function, and now we can try two. They have both the origin as their center, 0, 0, but a radius of 1 and a radius of 2. And again, we see we don't like too much having all these grid lines. We don't like too much having all these, the legend and all that. But before we take a look at all of that, let's just see how we can do many concentric circles. So now we use the center 0 for all the circles. The value r starts at point 1 and in steps of point 1 goes to 4. And if we plot all of those circles, it takes a while longer, of course, because we're doing a lot of circles. We get this interesting plot. So we don't like the plot circle and the grid, nor do we like the fact that it doesn't actually look like a circle. We have from -4 to 4 here and from -4 to 4 there, but we see that this -4 to 4 is actually a lot longer than this -4 to 4. And so what we do is we just say aspect underscore ratio equals 1. And when we do that, we get this lovely set of circles here. So we can now, instead of concentric circles, all of them with the same center, we make the center of a radius r at the x value r. So all of the circles will go to the origin. They'll be tangential at the origin to give us this lovely picture. Now, what we actually really want to do is to get the data, and the data in this case consists of comma-separated values in a file called practicedata.csv. We will pretend we don't know exactly what the format is, and we'll try and work out the format by using type of and size. So the first thing is to read it as a comma delimited file. So the comma delimitation goes out in single quote marks with a comma because it's a character. whereas practice.data.csv is a string, it's the name of the file, and that's why it's in double quotes. So the type of the data is an array with 2 dimensions, but that doesn't inform us very much. We know it's kind of like an array with rows and columns, but if we actually do this, we see that there are 2 rows and 100 columns. So we are thinking XY data, so the first row will be, say, the X data, and the second row will be, say, the Y data. So now we read in target X and target Y, and look at how we do this. That's target X, comma, target Y is target 1, comma, target 2, and target 1 is comma colon because it's all of the data in row 1, and that's all of the data in row 2. All of the data in row 1 go to target X. All of the data in row 2 go to target Y, and we get this. We plot it as scatter so that we can see the individual points and we don't get distracted by the lines that may join them. And we can see, yes, roughly it looks circular, but it's obviously a very coarse circle. Now we want to superimpose a circle on that. So let's see, -2 and 6 for the X and -6 and 2 for the Y. So the middle of -2 and 6 is at 2, and the middle of -6 and 2 is at -2. So that's our XY coordinate for the center, and from 2 to 6 is a distance of 4, so that's our radius. So we try our trial circle as center 2 minus 2 with a radius 4. Of course, first we put scatter, and then we bang the trial circle on top of it. And if we do that, we see that, oh, well, it's not such a bad circle, but actually it's not that great, is it? It's not quite in the right place, and maybe the radius isn't exactly the same either. So let's see. We don't need any new code. We can just go here and adjust this. So we need to shift it left a bit. So let's shift it to 0.1. But this blue line through here is probably in more or less the right place. So the center should also shift to the left slightly to keep this at the thing. In fact, it should shift left by the same amount. So let's make that 1.9. And it's slightly too low, so we must make this a bit negative. So let's make this 1.9 as well and see what we get. Well, it's still a little bit too far over. So we can make this 4.2, and we can make this 1.8. And now we see that the radius seems pretty good, but it should shift left a little bit more. Let's shift it left to 0.7. So we can compare it now and see. Now it becomes a fine adjustment. If we shift it up slightly, we would gain dots over here. There's quite a lot of dots on the edge that would go on the inside. And we would lose probably fewer dots. So let's lift it up a little bit and see what happens. We can shift it up to 1.8. And I wonder if we shouldn't shift it left slightly as well. Let's shift it left to 1.65, very slightly. It's beginning to be difficult to tell. So let's just look at this criterion of stopping. We could go on and on. You could wonder, you could actually really carefully start counting all of the dots on the outside, the dots that are half on the inside, half on the outside, they're just touching. But it becomes very difficult to tell. And basically you have to stop at some point. I'm going to stop now because I think it's very difficult to tell now for me whether it's better to make the circle slightly larger, slightly smaller, slightly higher, slightly lower, slightly left, slightly right. It seems as if it's close to the best possible, and I don't really know whether I can make it a lot better by spending a lot of time on it. So this is quite a subjective thing to do, but the point to notice is that stopping criteria for optimization are difficult. They have to be set to some extent subjectively, to some extent based on experience, but they're an art, they're a subjective thing, and that's unavoidable in numerical analysis, and so there's no reason for us to avoid it here. So we say that the best values we get by hand are approximately this, and we stop there. That solves the problem from the point of view of the peer review assessment. And that's the end of this lecture. Thank you.